So this is still chapter 17, which is expected value and standard error. And we're going to just review. So these are some extra problems to review. So first, a reminder of roulette rules so we can do our roulette problems. In roulette, we have 38 pockets. There's 18 red pockets, 18 black pockets, and 2 green pockets. So for example, 180, let's say we bet $1 on red 100 times in roulette. If you're correct, you win $1, otherwise you lose your dollar. So number one, how much money do you expect to win? Give or take how much? So we need to find the expected value and standard error. First though, we need to know what is our actual box model. So if we're doing something 100 times, it's going to be the sum of 100 draws from the box. And notice that this one we italicized how much money are we winning. So inside the box we want to put the amounts that we can actually win on a turn. So what are the amounts we can win? If you're correct, you win $1. So again, remember, inside the box, that's always just for one turn or one trial. Or you can lose your dollar, so negative $1. Those are our only two options. Now, how many of each of those tickets do we need in there? So we win $1 if we bet on red and we get red. So how many reds are there? There are 18 red pockets. So there's 18 tickets that give us $1. And then there's 18 black and 2 green, so that would be 20 tickets that make us lose. That make us have the negative $1. Now that we have our box model, we can go ahead and find our expected value and standard error. Notice that I did give you the average of the box and standard deviation of the box by using a calculator. So the expected value of the sum is equal to the number of draws times the average of the box. Number of draws, we have 100 draws. The average of the box is negative 0.05, so this gives me negative 5. For the standard error of the sum, now this is the standard deviation for the box. Because we only have 2 numbers inside the box, we could have used our shortcut formula to actually find this one by hand, but we don't have to because I told you the standard deviation of the box. I used the calculator and found the standard deviation of the box is 0.998. So this gives me 9.98 for my standard error. So what is our final conclusion? We expect to win about negative $5. So expect to lose about $5. Give or take $9.98. Do you notice how you're expecting to win a negative amount? That's how the casinos get their money. It may not be a lot of money that they're losing or they're actually winning per person, but if you play lots of times, eventually they're going to, the casino is winning more and more money. Now, so when you play 100 times, you're expecting to lose about $5, give or take $9.98. So it is possible that you might get $5, and you might even get even more, because this is probability and unlikely things happen. But overall, you can expect to actually lose money if you play 100 times. Now, what's the difference between number 1 and number 2? Number 1 says how much money. Number 2 says how many times. So this means, because it's how many times, this means we have to count. And remember, when we count, the only numbers inside our box are 1s and 0s. 1s for when we win, 0s for when we lose. So it's still going to be the sum of 100 draws from the box and what goes in the box. It's fairly similar, except for because we're just counting the number of times, we don't care about how much we actually win or lose, we're just counting the times we win. we just put in ones and zeros. So 1 means you win, and there's 18 ways you can win. 0 means you lose, and there's 20 ways that you can lose. Now we need to find the expected value for the sum and the standard error for the sum. But you might notice that I didn't give you the average and standard deviation in the box, so we are going to go through and find these by hand. So the average for the box is equal to, so I need to add it up, so 1 plus 1 plus 1 plus 1 18 times, or we can do a shortcut of 18 times 1, plus, and then I need to add up 0 20 times, so we could do 20 times 0. And divide by how many there are. There's a total of 38. So this gives me 0.47 is the average of my box. Now for the standard deviation of the box, this is where we get to use that formula. There's only two different numbers inside the box, so it's going to be big number minus small number times the square root of the fraction of the big number times the fraction with the small number. So my big number, 1, is bigger, so it's going to be 1 minus 0 times the square root. Fraction of the big number, that's 18. There's 18 tickets that have the big number out of a total of 38. And fraction of the small number, there's 20 tickets that had the small number of 0 out of 38. And this gives me 0.499. Now that I found the average and standard deviation, we can calculate the expected value of the sum and standard error of the sum. So expected value of the sum is going to be 100, so number of draws, times the average of the box. So 100 times 0.47 gives me 47. And for the standard error of the sum, it's the square root of your number of draws times standard deviation of the box, which gives me 4.99. Which is really close to 5. So what does this tell us? This means we expect to win about 47 times out of the 100, give or take 5 times or so. So we're expecting to win just a little under half. So even though we're winning, because we're winning less than half, overall, we're actually going to lose money like we saw in part 1. Now number 3 is, what is the chance that you win more than $10? Notice that we are now once again talking about the amount you win and not the number of times you win. And so this goes back to number 1. So our average is negative 0.5 and the standard deviation of the box is 9.98. Is negative 0.05 and the standard deviation of the box equals 0.998. Okay. So what's the chance that we win more than $10? So I guess actually we can come back up to number 1 and write down our expected value and the standard error. We don't need to calculate them again. The expected value of the sum is negative 5 and the standard error of the sum is 9.98. Now because it's a chance, we want to use the normal curve. We can only use the normal curve if we have a large number of draws, but we are talking about 100 draws, so that's a large number of draws. So our next step would be to standardize. So to standardize, you do the sum minus the expected value of the sum divided by the standard error of the sum. The sum we're interested in is we want the chance that you win more than $10. So the sum we're interested in is 10 minus our expected value, which is a -5, and divide by the standard error, which is 9.98. This gives me 1.50. So z is 1.50. We'd be looking for the area to the right because we want to win more than $10. So if we go to our normal table and we look up 1.50, it has 93.32%, but that's the area to the left because my normal table always gives me areas to the left. So 93.32 is the area to the left. We want the area to the right, so 100% minus 93.32% is 6.68%. So that's my final answer. Let's write it out. So we have a 6.68% chance of winning more than $10. Number 4, what is the chance that you come out ahead? So once again, we're following the same procedure. All we really need to do is find our new z-score. But let's just write down our notes. So the expected value of the sum is -5. The standard error of the sum equals 9.98. And we're looking for what is the chance? It says what is the chance that we come out ahead? So that means what is the chance that you win at least, or you win more than $0. So that's what we're really asking. So z, once again, is equal to the sum minus the expected value of the sum divided by the standard error of the sum. Now the sum I'm interested in is this $0. So 0 minus our expected value of -5 divided by the standard error of 9.98. This gives me about 0.5. So here's my z equals 0.5. I'm looking for the area to the right. If I look it up on my normal table, for my 0.5, the area to the left is 69.15. So we can use symmetry, so 100 minus 69.15 gives me 30.85%. So you have a 30.85% chance of coming out ahead, which isn't too bad. You might be willing to play those odds. For our next example, we have a true-false test with 20 questions. Each correct answer scores 5 points. Each wrong answer scores 0 points. If you guess all the answers, what is your expected score? Give or take how? So let's see, we have 20 questions, so the score is like the sum of 20 draws from the box let's see what goes in the box. A correct answer is 5 points. An incorrect answer is 0 points. Now it's true false, so you only have 2 choices. We only need 1 ticket of each. there's our box. Now you might have noticed that if you have the average of the box and standardization of the box, there's no reason for you don't even need to find the box to do these problems. But it is good practice for us to learn how to write down what the box is. Now we just need to find the expected value and standard error. So the expected value of the sum is equal to your number of draws times the average of the box. The number of the draws is 20, average of the box is 2.5. So this gives us 50. The standard error of the sum is equal to the square root of the number of draws times the standard deviation of the box. So the square root of 20 times the standard deviation, which actually happens to be 2.5 as well. That's just coincidence. So we get 11.2. Now what does this actually tell us? Statistics is all about what do these numbers actually tell us. So it tells us that your expected score is 50 points, give or take 11.2 points or so. Example 182, a child plays a game in which he has 30% chance of scoring 5 points, a 50% chance of scoring 3 points, and a 20% chance of scoring 1 point. If she plays the game 20 times, what is her expected score? Give or take how much? So once again, I did tell you the average and standard deviation in the box, so you don't technically have to write down the box model, but we're going to because this is good practice. So her score is like the sum of how many draws she plays the game 20 times, so 20 draws from the box, and let's see what needs to go into the box. Let's see, she can get 5 points, she can get 3 points, or she can get 1 point. Now it didn't tell us how many tickets are actually in there of each, it just gave us percentages. And so as long as you put in the correct ratio, that's fine. So let's say 30%, we can make that 30 tickets. 50% would be 50 tickets. And 20% could be 1 ticket. Now if you wanted, you could even do like 3, 5, and 2, as long as you keep the correct ratio. So 30, 50, 20, that would give us the correct percentages. Now that we've done all that, let's find our expected value and standard error for the sum. So expected value is number of draws, there are 20 draws, times the average of the box, which is 3.2. So this gives us 64. The standard error of the sum is equal to the square root of your number of draws times the standard deviation of the box, which is 1.4. So this gives me 6.26. So what does this tell us? This tells us that she can expect to get about 64 points, give or take 6.26 or so. Because remember, these are all chances, nothing is absolute. She might actually get 64 points, she might be 2 points under, she might be 8 points over, she might even be 10 points over. But she's most likely to be within this range of 64 points, give or take 6 points or so. So one more example. Let's say you bet 1 on a 17 100 times in roulette. If you're correct, you get $35. Otherwise, you lose your dollar. How much do you expect to win? Give or take how much? Once again, let's start with our box model. So the winnings are like the sum of how many draws. We're playing 100 times, so 100 draws from the box. And what needs to go into our box? Okay, let's see. We can bet $1. If we're correct, we get $35. Otherwise, you lose $1. So those are our only two choices, 35 or 1, or losing 1. Let's see, you can only win if you actually get the 17, and there's only one 17. You lose if you get anything else, and there's 38 total numbers, so we've one way to win, that means 37 ways to lose. Let's find the expected value of the sum. It's equal to the number of draws times the average of the box. So we did 100 draws, so 100 times the average of the box, which is negative 0.05, which is negative 5. And the standard error of the sum. Now, did you notice how this expected value is the same as the same expected value when we just bet $1 on red? So the casino must have this balance with their odds. That's how they decided that you should get the $35, as they were keeping the amount that you'd win about the same. But our standard deviation is different. Okay, now standard error for the sum is the square root of your number of draws times the standard deviation of the box. So this is the square root of 100 times 5.76, which gives me 57.6. That's a huge standard error. So what does this mean? So we can expect to actually lose about $5 since it was a negative winnings, but give or take $57.60. So notice that even though our winnings or losings in this case are about the same as when we bet $1 on red 100 times, how much you give or take is much higher. So the standard error was pretty high. This means there is a lot of possible variability. Because you are likely to be anywhere from losing, so if we do 5 minus 57.6, so negative 5 minus 57.6, anywhere from losing $62.60 to winning $52.60. That's a big range. So you might actually win a fair amount of money and be okay, but you might lose more money. So there's a lot of variability, there's a lot of maybe options, if you will, a lot of chances to get different results.